check.
Okay. I should probably first do the presentation and then share this screen. Right? Share this screen. A lot of people are online. Oh, good. Okay, so we are talking about electronic potential differences. So in an electronic field, what's the electronic potential at some point? That's, if you remember, what we are talking about. I need to go to slideshow here. Okay, we talk about these electron volts and then point charge, and then we talk about the superposition principle, and then we did the electronic dipole last time. Okay, and then today we're going to look at two more examples. One is ring, so let's look at the ring. Then this is a charged ring with a total charge of large Q. And then what's the electronic potential at P, this point, which is X from the ring, X axis. Okay, then do you want to do it, or should I do it? Do you want to calculate this? Or maybe I should do it. I feel sorry to pointing everything to you. Okay, so here, this is continuous charge, right? Continuous, it's not a point source. Then it's going to be integration. So KQ over R is a potential from a point charge, right? But then this is continuous object, so you integrate. And then, now, then K and R is not independent of X. So K and R, you don't need to integrate. Then DQ is, if you just integrate this DQ, it's just large Q. And then, okay, then R is this, right? R is X squared and A squared. A is radius and X is the distance. So R is X squared, A squared, KQ. So that's the charge. Does this make sense? It's easy, right? It's just integration. Okay, then next example. Let's look at the next example. So next example is this, not a ring, but now it's a plate. So there's empty in the middle, but then this is field. And then charge, total charge is still large Q. And then what's the potential, electronic potential at the point P? Then, so now we can just integrate. Okay, maybe I should go to the next page. So maybe I should go to here. So now we want to we want to find the electronic potential at P, and then now it's now again superposition principle. So the potential is integration from all the potential from all these different part of the disk. So it's integration over disk. And then now how we integrate is we consider small ring of the charge of delta Q. And if you consider small ring, then that potential is this, right? This is from the question 1 with that K dq x squared R squared. And then now we integrate this ring from 0 to A, radius A, then that's the whole disk, potential on the whole disk. So we just need to calculate this. And then how do we calculate this? It's Okay. So now the integration. So okay, to calculate, we need to figure out this area of the ring. Area of the ring is this length of the ring is 2 pi r, right? Say radius is r, the length of this ring is 2 pi r. And then width is dr. So if you multiply this and then this, so 2 pi r dr is the area of the small ring. Then the whole disk area, so this disk is uniformly charged to large Q. And the whole disk area is, of course, pi a squared, right? So the ratio, how much charges are here, that is needed here, dq. How much charge is needed here to the total charge ratio is the ratio of the area because it's uniformly charged. So this area, 2 pi r dr divided pi a squared, that's the whole area. So this area of the ring to the whole area of the disk is the ratio of dq and q. So we get this relation, dq is 2q divided a squared r dr. And then we need to put this in here to do the integration, because this integration is about radius, right? But this q is charged, right? So we need here dr. And then how to convert this dq to dr is using this. And then we put this in here, and the integration becomes something like this. Now it becomes r dr, so integration becomes r. And then those constants, we put it outside, and then we just integrate about r, right? R here. And then, okay. Now we need some mathematical technique to integrate. Then now, okay, we know this and then this. So then if we replace this part, so this part is complicated, right? So we replace this part as new parameter, then integral is like this. How do you say it? This is replaced integral or something like that, right? You learn in high school how to do this. Then if you integrate this, then it's going to be like this, and then put this 0 and a, and then it becomes this and then this. Is it okay? You integrate this, and then it becomes this. Is it okay? Because this 1/2, it cancels with 2, right? So this becomes this. And then put number 0 to a, and it becomes this. So that's the answer. Is it? It should be, right? Should be. Yeah, so that's the answer written here. Okay, and then now we compare these two. So now we compare these two, and then this is, which one is, so this line, this equation, if you plot it, it's like this. And then point charge potential, Q over R, is this. And then if you do I thought we did it a while ago, but infinite sheet potential is going to be this. So this disk, if you're looking at this in a very close distance, then it's very similar here. It's very similar to the infinite sheet, right? Because if you are very close to here, then it looks like a sheet. So it makes sense. And if you go far away, if you move far away from here, then it looks like point source. That makes sense, right? If you're very, very far away from the disk, even though it's a disk, it looks like a point source, right? And then potential also looks like point source. So that everything makes sense. Okay, any questions so far? Wei-Lin, did you get everything? or you're sleeping. Okay. Then let's go to next. Electronic difference and the electronic field. Potential difference involves an integral over the electronic field. That's what we did, what we have been doing. So the field involves derivative of potential. So, it's the opposite, right? If you integrate electronic field, you get electronic potential. So that means if you take a derivative of the potential, you get electronic field. It's the integration and derivation, the relation, right? And to be specific, the component of the electronic field in a given direction is negative of the rate of the charge of potential in that direction. So the change of the potential is electronic field. So then if you're given potential V, which is a scalar quantity, as a function position, then electronic field follows if you take a derivative in for example, XYZ direction of the potential V, you get electronic field. Derivatives here are called partial derivatives because it's direction, X, Y, Z direction, expressing the variation with respect to one variable alone. So in that direction, X, Y, X or Y or Z direction. This approach may be used to find the field from the potential. The potential is often easier to calculate than electronic field since it's a scalar rather than vector. Okay, does it make sense? It's like a mountain, right? Say mountains of potential, then electronic field is the slope, how slope it is, and then say how much the height of the mountain is changing, then that gives you electronic field, how much slope you are climbing. If it's changing rapidly, then slope is very steep. Okay. Okay, maybe I should have mentioned that here. So equipotential is the surface on which potential is constant. So something like this. So this dotted line is potential is the same, or height is the same. Then this is equipotential line. Then in two-dimensional drawing, we represent equipotential by curves similar to the contour. So this is in 3D, but in 2D, you just equipotential is these circles written here. Electronic field is always perpendicular to the equipotential because these are potential and electronic field should be perpendicular, in a direction where potential changes. The figure, okay. This is a charged spherical field because it's a shell. Charged spherical shell. So that's why potential is zero inside. Electronic field is zero inside. The figure below shows the equipotential for dipole. If it's dipole, it's more complicated, right? Because there's a plus and minus. That figure is very similar to the mountain example. Charged conductors. Okay. There's no electric field inside the conductor in electrostatic equilibrium. So conductor is something like that current can go through. So that means inside here charges can move around. So this is something like a metal block, then charges can move around, right? Electrons, and then sometimes positive charges can move around. Then because inside these conductors charges can move around to cancel the electronic field, so that's why electronic field is always zero inside. For example, if there's an electronic field, then say, I don't know, this direction, then that's going to move the charges so that it cancels the electronic field. So that's why it's always zero inside. And even at the surface of the conductor, there's no field component parallel to the surface. So even at the surface, there's no electronic field parallel to the surface, because if there's an electronic field like this parallel to the surface, then that's going to move the charges to cancel out that electronic field. It's the same thing. So conductor, inside the conductor is equipotential, and then, okay. So this means equipotential is at the surface, near the surface, it's very similar to the shape of the conductor. That makes sense? Okay, and then, so that means that generally makes the equipotential closer. So say look at the peak here. Here, if there's a peak, there's a sharp peak, then this equipotential is going to get closer here because it's sharp, it gets closer. Then that means electronic field is stronger and the charge density is higher. So you can tell, right? Here, equipotential is denser compared to here. So that's why if you want to do something, electronic laser or something like that, then it have a very sharp edge right here to make the potential higher, electronic field higher. Sorry. Okay, so that's what we talk about in this chapter. We talk about what did we talk about? We talk about electronic field and electronic potential, and then we talk about superposition principle, equipotential. Okay. Maybe we should watch this. So the laser printer, it's something that using this. Okay. Yeah. So I talk about this, right? So in a sharp edge, electron field gets stronger. So the laser printer uses that to print things. Maybe I can click this. How am I going to click this? Okay, I think I should stop the slideshow first. Okay. I always see this Uber's advertisement. I need to, no, this is no, I want to show this one. You see that? Can I make a sound here? How do I? I need to know my speaker first. Okay. How about microphone?
All of which occur within the cartridge. Let's start laser technology.
Let's.
What an assembly of more than 80 different components. Performance engineered exclusively for the printer for which it was designed. It's the heart of the printing process. How does a laser printer transform characters into hard copy? There are 6 distinct processes involved in producing a laser printed page, all of which occur within the cartridge. Lexmark laser technology uses an electrophotographic process to transfer digital data to paper. The process begins with the charge roller, which applies a uniform charge to the surface of photoconductor drum. Photoconductor drums are highly sophisticated components, precisely formulated to the power and wavelength of the laser print engine for which they are designed. The laser strikes the photoconductor drum up to 65 million times a second, creating a chemical reaction that discharges the areas that are negatively charged, resulting in an electrostatic image. Next, the image is developed. The toner adder roll coats the developer roll with toner while electrostatically charging the particles. As the toner is placed on the developer roll, a leveling device called a doctor blade evens the toner to a thickness of approximately 15 microns, just slightly thicker than a strand of silk. As the developer roll and photoconductor drum come into contact, the negatively charged toner is attracted to the discharged areas of the drum. When the paper passes under the drum, the transfer roller applies a slight electrical charge, causing the toner to move from the drum to the paper. The drum rotates up to 2 revolutions per second, timed with the exact speed of the paper, ensuring a complete image transfer. Next, the image is made permanent through a combination of precisely controlled heat and pressure. As the paper approaches, the fuser rollers heat up to 225 degrees Celsius. In just 23 thousandths of a second, the powdered toner reaches its melting point and bonds onto the page. The melting point of Lexmark toners are specifically for...
Okay, so just like we're talking about that, if I understand correctly, I should mute this, right? So using this very sharp edge where electronic field is very strong, then they curve the letters onto the drum, and then the part where you want to print, say you want to print these kind of letters, then these part is I think positively charged, and then toner is negatively charged. So when toner comes in, only these charged parts need to be printed. That's how the laser printer works. Okay, so that's the end of this chapter. So maybe we can have a 10 minutes break here, and then we start at 9:25. Okay. Okay, any questions? No? If not, please come back at 9:25. Okay, maybe we can stop one time.